Let's finish this lesson and the unit off with a discussion of differentials and a tangent plane, or a linearization is another name for a tangent plane. But first, let's review the tangent line linearization that we talked about last year in BC Calculus. So based on this diagram, we have the function, let's just write up here, y equals f of x. And we have a tangent line to the function. So of course, this corresponding point here would be f of a. All right. If you recall, delta x and dx both refer to a change in x. They both mathematically are the same. They are the difference in x values. Delta has the connotation of large, and d has a connotation of very small, incrementally small. And one of the things we talked about is that our delta y can be approximated with a dy, and so the dy here is this distance here, and if you physically plug in a plus dx into the line function and then subtract f of a, you see that dy is going to be f prime of a dx. And remember, dx and delta x are interchangeable. So one of the things we say here is that delta y is approximately dy, which equals f prime of a dx. We could also say that delta y is approximately dy, which equals f prime of x, to make it more general, times dx. It would be wrong to say that delta y is equal to dy, or delta y is equal to f prime of x delta x. That would be wrong. See, delta y is this entire difference, and that includes the dy portion plus this portion here, which we could say is some error. So we might say it like this: delta y equals f prime of x dx plus some error. So now the idea here is that when delta x is approaching 0, then we give it the connotation of dx, and let's see if we can visualize that. Take x and go closer to a, or in other words, collapse delta x to be very, 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 very small. Then you can see that the delta x can be written as dx, and it also tells us then that the error goes away. As we get incrementally small, this error term here goes away, and then we are led with dy equals f prime of x dx. So that's no different than we already stated in the beginning, but that's just another way of thinking of it. So now in a tangent line linearization, we showed that dy was equal to f prime of x dx, and that dy can be used to approximate delta y. So now if we think of a tangent plane to a surface, let the surface be z is a function of x and y, then you should get the general sense that df, or dz you might say, is equal to some x slope times the dx, but then you have a y change, which would be the y slope times the dy. Now I'm going to write this a little differently. So I'm going to say that delta f is equal to the x slope times delta x plus some error in the x direction plus fy times delta y plus some different error in the y direction. And as the delta x and the delta y both go to 0, then the error terms go to 0. The delta x then approaches the dx, the delta y approaches the dy, and then the delta f approaches the df. And so we can say here that df equals f partial derivative with respect to x, so the x slope times dx plus the y slope times dy. And this looks a lot like the chain rule that we discussed. So if I wanted to find dz with respect to x, then we can think of that as fx times dx dx plus fy times dy dx. Or perhaps I do it with respect to some other variable. So dz dt then would be fx dx dt plus fy times dy dt. Do you see the chain rule there? It's dz dt equals par f par x times dx dt plus par f par y times dy dt. Now I would like you to read this section of your textbook. It is section 14.4. I would like you to read it over. It's going to have some better diagrams, some better explanations, more thorough explanations, and you may need to read the section in order to solve all the homework problems.